In this video, we're going to assess normality. In the examples that we have seen previously, we have been told that a distribution of data follows a normal distribution. But how do we know if a set of data is going to follow a normal distribution or not? Oftentimes when we have real data, it's not certain that we'll have a normal distribution. So we need a way of assessing whether or not we have a normal distribution. And one method that we can use to determine this is a method called normal probability plots. So we can create a normal probability plot, and to do that we'll use this process. Okay? Step 1, we're going to arrange the data in ascending order. Step 2, we're going to compute f sub I equals I minus 0.375 divided by n plus 0.25, where I is the index, which means the position of the data value in the ordered list, n is the number of observations, and the expected proportion of observations less than or equal to the ith data value is f sub I. So in other words, this f sub I is the area to the left of the data value, or at least it is the area that we would expect to be to the left of the data value if the data value is following a normal distribution. Step 3, we're going to find the z-score that corresponds to each f sub I from step 2. We're going to use either table 5 from the appendix of our book, or we can use technology to figure that out. Step 4, we're going to plot the observed values on the horizontal axis and the corresponding expected z-scores on the vertical axis. Okay, so we're going to create ordered pairs by using the actual data value and then the expected z-score. Now, if the sample data are taken from a population that's normally distributed, then a normal probability plot of the observed values versus the expected z-scores will be approximately linear. In other words, these points should be linear if the data comes from a normal distribution. If the points aren't linear, then the data probably don't come from a normal distribution. Now, of course, there's never going to be perfection, so the points will never be perfectly linear. We just need them to be approximately linear. So let's look at an example. So consider the following data values. So we have the data values 15, 5, 20, 2, 9, 7, 11, and 19. And we want to know, is there evidence to support that these data are normally distributed? So in order to determine this, we are going to find or make a probability plot, a normal probability plot. Okay? So the first thing I have to do is put these data in order from smallest to biggest. So I'm going to just arrange my data from smallest to biggest. So the smallest data value we have is 2. The next smallest data value we have is 5. And then 7, and then 9, 2, 5, 7, 9, then 11, then 15, then 19, and then 20. So we have 1, 2, 3, 4, 5, 6, 7, 8 data values, and we've put them in ascending order. So next I'm going to find the index for each one of these. So the index is our value I. And so I'm just going to number them. 2 was the first data value, 5 was the second, 7 was the third, 9 was the fourth, and so on. 5th, 6th, 7th, 8th. So here are our data values. Okay, these are the index values for each of our data values. Okay, so next I'm going to find the area that should be to the left of each data value. In other words, I'm going to find f sub I. And f sub I, based on our formula, is I minus 0.375 divided by n plus 0.25. N, in our case, is 8. Okay? So using that for our first data value, the index is 1. So f sub 1 would equal 1 minus 0.375 divided by 8 plus 0.25. Now, if I use my calculator to calculate that, 1 minus 0.375 divided by 8 plus 0.25. Notice I had to put those in parentheses. Then that gives me 0.0758 if I round to 4 places. So this is about 0.0758 approximately. Okay? F sub 2 would be 2 minus 0.375 divided by 8 plus 0.25. So if I pull back in my calculator and recalculate, I'm changing that to 2. So that area would be 0.1970 if I round to 4 places. So 0.1970. F of 3, if I continue, I'm not going to write the formula, but it would be 3 minus 0.375 divided by 8 plus 0.25, and that area is 0.3182. So this would be 0.3182. F of 4, same deal. And so that is 0.4394. F of 5 is 0.5606. F of 6, F of 7, F of 8. So those values are going to be 0.6818 for F of 6, 0.8030 for F of 7, and 0.9242 for F of 8. Okay? So now I can find the expected z-scores. So the expected z-score is going to be the z-score that has 0.0758 to the left, 0.1970 to the left, and so on. Okay? So if I do inverse norm, just continuing to use my calculator, I could use the table, I could use StatCrunch to find these as well. Okay? So inverse norm of 0.0758, mean of 0, standard deviation is 1, that's the area to the left. And so that z-score would be about negative 1.43. Next, the area is 0.1970, and so that would be about negative 0.85. Next, 0.3182 is the area to the left, so that z-score would be negative 0.47. Next, 0.4395 is the area to the left, so that is negative 0.15. Next, the area is 0.5606, and so I get positive 0.15. Next, the area to the left is 6816, and so I get positive 0.47. Next, we get 8030, and so that is 0.85 positive. And last but not least, 0.9242 is the area to the left, and we get positive 1.43. So we have our actual data values that were here, and we have the expected z-scores if these data come from a normal distribution. Notice the symmetry of the z-scores. So negative 1.43, positive 1.43, negative 0.85, positive 0.85, and so on. That will always happen for the expected z-scores. Okay, we should always have that kind of symmetry. Now, next we want to create the normal probability plot. So I'm going to do that on a separate sheet. So I'm going to make coordinate axes here. So along the horizontal axis, we're going to use the actual data values, and along the vertical axis, we're going to have the expected z-scores. So these are the z-scores that we would expect, okay? Now, our data values range from 2 through 20, so maybe I'll go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And then our expected z-scores, I should have left a little room here, but I'll write these in. We're going from negative 1.43 to positive 1.43. So I'm going to make this 0. I'm going to go on the outside of my label here. So there would be 0. So maybe here would be negative 0.5, negative 1, negative 1.5, negative 2. So negative 0.5, negative 1, negative 1.5, negative 2. And then here would be positive 0.5, positive 1, positive 1.5, positive 2. So 0.5, 1, 1.5, and 2. And again, I really should have put my label on the outside of that, but I wrote that prematurely. Anyway, so now looking at our results back on the previous page, our data value 2 had an expected z-score of negative 1.43, so we're going to plot that point. 2, negative 1.43 would be around there, okay? Our data value 5 had an expected z-score of negative 0.85. So 5 would be around here. Negative 0.85 would be maybe around here. So we have that point. Our data value 7 had an expected z-score of negative 0.47. So 7 would be here. Negative 0.47 would be around here. Our data value of 9 had an expected z-score of negative 0.15. So 9, negative 0.15 would be maybe around here. Data value 11 had an expected z-score of positive 0.15, so 11 and positive 0.15 would maybe be around here. 15 had an expected z-score of 0.47, so 15's over here, 0.47 would be maybe around here. 19 had an expected z-score of 0.85. So 19 would be here, 0.85 would be maybe around here. And then last but not least, our expected value 20 had an expected z-score of 1.43. So data value 20, 1.43 would be maybe around in there. Okay? So here is a very roughly sketched probability plot, normal probability plot. So do these look linear? Well, they look pretty linear. And so yeah, this looks like we have a pretty linear relationship. But what if we can't tell for sure if this looks linear or not? Well, one way that we can determine for certain if this is a linear relationship and thus would indicate that our data comes from a normal distribution is by finding the correlation coefficient. Okay? So if I want to find the correlation coefficient, then I can enter the data values along with the expected z-scores into my calculator or into StatCrunch and find the correlation coefficient. So if I bring in my calculator, now I have entered my data values along with their expected z-scores into list 1 and list 2 into my calculator. And I'm going to do a linear regression to find the correlation coefficient. So if I go back to the home screen, I'm going to do stat and calc and linear regression. My x's are in list 1, my expected z-scores are in list 2. And so if I calculate, I see that I have a correlation coefficient of 0.9844. So the correlation coefficients for this relationship between the data values and the expected z-scores is 0.9844, which is very, very close to 1, which would indicate that we do have a linear relationship. But what if this correlation coefficient hadn't been this close to 1? What if it had been, say, 0.8844 or 0.7844? Would that be close enough to say that this is linear? Well, we have a table of critical values that we can use for this. This is table 6 from the appendix of our book. And so if I bring this in, here's how this works. So I look at our sample size, which in this case was 8, okay? And so our critical value is 0.906. As long as our correlation coefficient is 0.906 or higher, that indicates we have a linear relationship, and thus our data follows a normal distribution. Okay? So if I compare our correlation coefficient to the critical value, and again that critical value is 0.906, our correlation coefficient is larger than the critical value, so that indicates we do have a linear relationship, and it indicates that these data come from a normal distribution. So these data, 15, 5, 22, 9, 7, 11, and 19, do come from a normal distribution. So is there evidence to support that these data are normally distributed? The answer to that question is yes. Okay? Now, as you might imagine, we do have some technology methods that we could use as well, and so I want to discuss those as well. So I'm going to bring in my calculator again, and I'm going to go to Stat and Edit, and I'm going to clear out the expected z-scores that I had typed in from before. Okay? What I have in list 1 are the data values. Now I have these in order from my previous work, but you do not have to put these in order. Now our calculator can do a normal probability plot, but what it can't do is it can't tell us the correlation coefficient. Okay? So let me discuss this. If I go to Second and Stat Plot, I'm going to choose a plot and turn it on. Now this last icon, the one farthest to the right, is a normal probability plot. Okay? So what I have to tell the calculator is that I want to do a normal probability plot, so I've chosen that icon. My data is in list 1. Okay? Now the data axis, when we create our normal probability plot, we can put the data along the x-axis, or and if we put the data along the x-axis, then the expected z-scores go along the y-axis. Or we could do it the other way around. So we could put the expected z-scores along the x-axis and the data along the y-axis. We're always going to do it along the x-axis. We're going to have the data along the x-axis. Choose the mark and the color if you have that option. Now I'm going to choose Zoom and 9 so that the calculator will pick a window for me. And so this is the normal probability plot, which does in fact look pretty linear, and so it would be pretty good evidence that we do in fact have a linear relationship, which means that our data does come from a normal distribution. However, the calculator does not tell me what the correlation coefficient is, so if I want that, I still have to determine that separately. If I trace this, I do want to point out some discrepancies. So the expected z-score for the calculator for the data value 2 is negative 1.53. Now for our 2, we came up with negative 1.43. The calculator says the expected z-score should be negative 1.53. Likewise, for 5, we got negative 0.85. The calculator says negative 0.887. For 3, we got negative 0.47. The calculator has negative 0.488, and so on. So for all of our z-scores, the calculator has different expected z-scores than what we came up with. Now, why is that the case? Well, that happens because of our formula. So we used this formula right here in order to calculate the area to the left and ultimately to determine the expected z-scores. Well, truthfully, this formula is a somewhat simplistic formula. The formula that the calculator uses is a little more complicated, and so it comes up with different expected z-scores as a general rule because of that. Okay, and so that's why there's that discrepancy. There's not much we can do about it, but I just wanted to point out that there was a discrepancy. Now, in closing, we can also do a similar kind of result in StatCrunch. But StatCrunch, unfortunately, does not have the capability of doing a normal probability plot. So looking here at StatCrunch, if we go to graphs, we do not have a normal probability option. Okay? Now, by the way, I have entered the data into StatCrunch here. So here were our 8 data values that I've entered into StatCrunch. Again, StatCrunch does not have the option of a normal probability plot, but it does have something pretty similar called a QQ plot. Not exactly the same thing, but pretty close. Okay, so I've selected QQ plot, and I have to tell StatCrunch where the data are, and so they're in this column called var1. Okay, now if I say compute, then StatCrunch calculates this QQ plot. Okay, now QQ plot is similar to the normal probability plot, but instead of using expected z-scores, it uses something called quantiles. Okay, now just to be clear, by default, it puts the expected quantiles on the horizontal axis, and it puts the data values on the vertical axis. But we can change that so that it will match our normal probability plot. So in the options, I generally am going to select put the normal quantiles on the y-axis. So put a check mark in that box. That way it puts the expected z-scores on the y-axis and the data values on the x-axis. I can also check this box so StatCrunch will calculate the correlation statistic for me. So when I recompute, now this looks a little bit more like our normal probability plot because now we have the data values on the x-axis and we have the expected quantiles on the y-axis. So if you make a comparison, it looks very, very similar. Also notice that we have the correlation statistic here, which is 0.988. Now that's not exactly the same correlation coefficient that we got here in our problem. We got 0.984, but as a general rule, they're going to be very close. So if I compare 0.988 to our critical value 0.906, it's larger, which indicates the data are linear, which indicates that the data do come from a normal distribution.